Hello. Good morning. Good afternoon, Kanchana. Nice to see you.
Afternoon, sir.
So now shall we start the session?
Yes, sir.
Hello, good afternoon, participants. I hope you had a very leisure time since morning because it is just the second session of the day. Unfortunately, we were not having a second session, that is from 11 to 12, because of our colleague from CMTI, the scientist F from CMTI, Dr. S.K. Verma. He is not feeling well, so he could not able to make it in the morning. Let me see if possible he can make it on some other day. So now I welcome all of you to join the new session of the afternoon. Uh, you are lucky to hear one of the good researcher in mathematics. So I introduce Dr. Kanchana. She did her PhD in 2017 from Bangalore University. Then her awards speak out about her ability. In 2016, she got Young Scientist Award on 61st Congress of Islam. That was held at VIT, Vellore, India. Then in 2013, she got Rajiv Gandhi National Fellowship Award. Then she got first rank in 2012 in mathematics for Bangalore University. She is a gold medalist. She won six gold medals in MSc. Then she visited several countries. Among them, the important one are China. She went there to present her paper. In Cambridge University, she attended summer school on fluid dynamics of sustainability and environment. And in University of Putra, Malaysia, she went there as a PhD mobility student. Then she went to US to present a paper in Pacific Rim Thermal Engineering Conference. So she has got very vast publications and she has got very good uh, published in very good papers like Physics of Fluids. Recently, I heard that she is getting her paper in JAM also. She has got a very good citation index. It is 153. I-10 index is 10. H index is 6. With this, she is now working as a research expert in University of Tarapaca, Chile. Now I hand over the session to her. It is over to you, Kanchana.
Thank you, sir. Thank you for the introduction. Now I shall share my screen. Will you please let me know whether it is shared? Is slide is visible, sir?
Yeah, it's feasible.
Okay.
Yeah, visible.
Good afternoon. Okay, sir. Thank you. Dear participants, hello. I think I am audible to everyone.
Yeah, it's visible.
Okay, sir.
Uh,
Thank you.
Prakash, please
Yes, sir.
mute your microphone.
Thank you, sir.
Yeah.
Uh, Dear participants, I would like to explain about chaotic hydrodynamics. You might already heard about chaotic in the morning session. That is when chaos occurs, how it would be. You might have heard from Home P. Sudhar sir, and he also explained the phase space diagram very nicely and the sensitive to initial condition very nice way. In this session, I would like to explain the topic which Dr. Home P. Sutta didn't cover. That is, once chaos occurs, is the system will be stable in the chaotic motion itself, or is it undergo any other motion? That we will see in this session. And other thing is, when chaos occurs, the chaos may be, um, though it is sensitive to initial condition, we need to study this not only in phase space diagram, because once chaos occurs, um, after some time, maybe after some range of hour, the value maybe changes. After we cannot predict at which value of r the change behavior of chaos changes. For that we need to go for two things. One is Lyapunov exponent and another is bifurcation diagram. So these two methods are, maybe it's a plot, okay? By using those plot, we can study the behavior of chaotic, and is the chaos, the system will be in the chaos, or it may change to some other motion, that we can study using those two methods, that is Lyapunov exponent and bifurcation diagram. So, as so mentioned, I am now right now working as a research expert in the University of Tarapaca under Professor Lagos. I would like to mention few things about Professor Lagos here. Actually, his field is chaos, and he has a very good laboratory in Chile, so we can do many computation there. And I will show you some plots and I will explain you how you can get that plots and how much effort and time required for that. In fact, few plots we cannot do by our normal system, that I would like to emphasize there. So the problem which I'm going to explain you is already published in Communication in Nonlinear Science and Numerical Simulation paper, and this I did with Professor He Zhao. He is a professor of mathematics in Harbin Institute of Technology, China. I did postdoc under him last 3 years, and I also guided a student of him. So it's a collaboration of ours. So you already know about this diagram, I think, that is Rayleigh-Benard convection, how it occurs and all. I just explain how one can transit from the convection to chaotic motion. As you know, the convection sets in when if we increase temperature delta T at particular temperature, say delta Tc, we will see like this some cells. We usually call it as Benard cell because this was first time observed by Benard while doing experiment. And we usually study stability analysis, linear stability analysis, weakly nonlinear stability analysis, and even energy method, energy stability analysis nearby this threshold. That is when the convection occurs, that is the cell forms. Okay, suppose if you eat further after delta Tc, if you eat further with uniform heat, okay, then after some time, that means after some temperature, The cells are no more exist, and we can see some motion, and we cannot predict what kind of motion for the system. So that kind of motion or behavior in the fluid we call chaos or chaotic motion. So when the transit from this regular motion to chaotic motion occurs is very difficult to predict, and I think it is unpredictable, and hence we call it as aperiodic motion. Chaotic motion is always a aperiodic motion. So morning, Om sir is explained how it will be. Now I would like to explain that in mathematical way. Okay. So while deriving Lorentz model, we need to assume these three things. So Oberbeck-Bosniak approximation, very well explained by Sir Om sir. Then we consider only two-dimensional, that also he explained. So the region of interest, our region of interest is axis from minus infinity to plus infinity. That is, we will take a horizontal extension like this. X ranges from minus infinity to plus infinity. Within that, there are many rolls, and those rolls are anti-clockwise and clockwise. This is because of friction. This is already from Professor Siddeshwar. And we call this entire cell, here, two cells. That is, one is clockwise, another is anti-clockwise, as one wavelength. Okay, and Z ranges from 0 to H. So this region of interest we are going to study here. And we also assumed small scale convective motion. That is, we won't consider acceleration term in the linear momentum. And due to Bosniak approximation, density is constant everywhere except when it is with body force, where rho is function of T, that is temperature, which is given by equation of state, this equation number 4. And you also know how to do linear stability analysis from the morning session. So I directly go for nonlinear stability analysis. In the nonlinear stability analysis, we are considering only minimal mode, that is amplitude A, B, and C. Why can't we go for further modes? We can do by using further modes. We can increase modes in psi as well as in theta, but it's already done by Saltman and showed that the linear stability analysis, that is nearby threshold, the behavior of the fluid won't change though you increase the number of modes. That's why we consider the minimal one. And the minimum mode for linear stability analysis is only this A, amplitude A and B, only these terms, except this. This occurs only for non-linear stability analysis. Okay. But recently we are going through for higher modes. If we had higher modes, there is change in chaotic motion. There is no change in regular motion, but there are some changes in chaotic motion that I did not cover in this session because the work is undergoing. We may discuss this later in some other occasion. Okay. But as far as linear stability is concerned, they won't change when we had modes. That's why we usually take normal mode or minimal truncated Fourier representation as a solution for the governing equation that I already showed, that is equation 1 to 4. And scaling, that is very important here. The scaling that the Lorentz and Salzman took is nothing but RA versus RA critical. This represents the critical of the RA critical, that is the value of RA at which convection formation of rolls occurs. So the derivation I skip because it's already done in the morning session. So once you substitute that equation solution 5 and 6 in the governing equations and using standard orthogonality condition, you will get the Lorentz system of the form equation 7 to 9. It's a classical Lorentz system. We already done the same study for rigid boundaries where we come with for each term there must be some constant, okay, and we already done this problem for modulation and also some modulations like rotation, gravity modulation, and many things, ferrofluid, nanofluid, everything. But the idea for choosing the classic one in this session is you must understand how this chaos one can study so that you can apply this problem to your own problem that you are going to do, you are doing in your thesis, or some maybe you are in future. Suppose if you want to do something, you can refer this as a basic, a fundamental one. That is the reason I took a classical Lorentz model instead of some other tricky problem. So if you substitute in the place of amplitude A, B by minus A and minus B, you will once again get back the same Lorentz equation. You might have done this and you read this in many papers. So the Lorentz model is symmetric and it is invariant under the transformation that we know. But this is a very useful feature of Lorentz model. How that I will explain you in the next session, next slide. So at steady state, we will get critical point as 0, 0, 0 and other two. And we call this 0, 0 as a pre-onset critical point and this is a post-onset critical point. This is because I already told you how I defined R. R is nothing but capital RA, that is Rayleigh number versus critical Rayleigh number, and it takes value 1 when the Rayleigh number is critical Rayleigh number. That means this critical point occurs after formation of cell, that is after onset of convection. Whereas 0, 0, 0, this critical point, suppose if you, it will occur in the when R is less than 1 also. So it is a pre-onset critical point. And the stability analysis around these critical points will explain you the nature of the solution. Okay, the phase space diagram that you have seen in the morning, a time series plot that show the chaotic behavior, right? But without plotting that, just studying the stability around the critical point, one can decide on how the solution will be without plotting. And as I mentioned earlier, the Lorentz system is symmetry, and that is very useful information because of the symmetry, we are getting post-onset critical point in this way. Okay, and we can classify those critical points as center, stable node, stable spiral, and unstable node, and unstable spiral, and saddle point. When the solution approaches to the critical point, then we say it is a stable node. When the solution amplitude approaches, so going away from the critical point, then it is unstable node. When it spirals inside or inward, then it is stable spiral. When it is outward, spirals outward, then unstable spiral. So these all are basic things, and one should know. And I don't have much time to explain each of the one, so I have mentioned the references for this very good book, Simon's In that you can find out some examples with for each this classification of critical points. Now in this session we will see the nature of all these three critical points, and since the Lorentz model satisfies this symmetry, so if you see the nature of any one of these two post-onset critical points, that is sufficient. So we will go with any one of this post-onset critical point, then pre-onset critical point, and we will see the nature of the solution around these critical points. Okay. To do so, there is some procedure. So I'll explain that. Let us take amplitude A, B, C has A1, B1, C1 plus those critical points. That is A naught, B naught, C naught. Yeah, A naught, B naught, C naught is a critical point 0, 0, 0. That is pre-onset critical point. And substituting that in the Lorentz system, you will get the amplitude in terms of A1. And if you see these three equations, you can easily find out equation 20. Last equation is uncoupled. So the solution of this you can easily guess. It must be of the form equation 21. And from this you can easily say as tau, that time tending to infinity, the solution C1 amplitude is tending to 0. That means it is going in near the critical point. It's a stable node. Okay. And for other two, let us assume solution as 22, and by substituting equation 22 in the Lorentz system, yeah, that is 18 and 19, we will get homogeneous equation in terms of A10, B10. This is also an amplitude, mind you. So solving this determinant, we will get auxiliary equation. Okay. And the auxiliary equation is a quadratic, so you will get a roots, and this root, by seeing the nature of this root, we can decide whether it is a node, saddle point, spiral, or center. And once again I would like to tell you here about the detail about these things you will get in the Simon's book. You can go for it. Okay. The roots, suppose the two roots are real, distinct, and of same sign, then the critical point is node. How? You will get it from that book. Okay. Then similarly, if the one root is, if both roots are real, distinct, and opposite sign, then it is a saddle point. If both roots are conjugate complex but not purely imaginary, then the critical point is a spiral. If both roots are purely imaginary, then it is a center. So by seeing the nature of the root, we can decide whether the solution is a node, saddle point, spiral, or center. Okay. And if you see equation 26, we can find a value for, we can fix a value for Prandtl PR, that is Prandtl number. If you choose a fluid, then you can get a Prandtl number. So for example, for water, Prandtl number is around 6, but Lorentz took 10. So I will also taking 10 in the problem. But we need to vary R, the scale Rayleigh number, we need to vary. So I have done that here. So I just made some plotting. Okay. I plotted the roots for different R, and I got it that when R is less than 1, it's a stable node. We already showed that. That is, these two both are negative. And when R is 1, it is approaching origin, so saddle point. If R is greater than 1, it's a stable saddle point. Similarly, we can do the stability analysis around the critical point, that is post onset critical point. Okay, same procedure. Once again, I'll take a b c as a2 b2 c2 with the plus the critical number, critical point, sorry. Then linearizing the system around the critical point. Here I cannot assume, I cannot uh, take the last one separately because all are coupled. So I'll assume solution of amplitudes as this form, equation 29, and substituting the solution into the equation, you will get the all param here a2 b2 as alpha beta gamma in terms of alpha beta gamma into mu. Okay, and eliminating alpha beta gamma from the equation 30, we get a cubic polynomial in terms of mu. And once again, we know PR B, and for different value of R, we will see the nature of the critical nature of the system around the critical point. And I also found that roots, okay, and this is by Simon's book. Suppose the three roots are real, distinct, and of same sign, then the critical point is a node. Suppose three roots are real, distinct, and of a different sign, then the critical point is a saddle point. Suppose one root is real and other two roots are conjugate complex but not purely imaginary, then the critical point is a spiral. If it is complex conjugate and purely imaginary, sorry, if it is purely imaginary and real, the one root is real and two roots are purely imaginary, then it is center. Okay. So for different values of R, I calculated by substituting PRB, mu1, mu2, mu3, and I found that when R is 1, mu1 is 0, mu2, mu3 are real, and we already showed that it is a stable node approaching, okay, approaching to origin. For other values, it's a spiral. Okay, but if you see after some value that is 24.8, it is going towards purely imaginary. Okay, so it is a saddle, and this will give you the RH, that is Hop Rayleigh number, that is the transition from regular convective motion to chaotic motion. So R is equal to 1 is a regular convective motion after certain value of R. That means after heating the bottom plate, after uniform heating of bottom plate at, up to some time, then it reaches to the chaos. So this entire value, that is region, if you take it in the plot, okay, is called a transition time or transition region. And if you take the sum of these roots, it is constant throughout and minus n. This indicates dissipative nature of the system. So one way of showing dissipation is this. There is another way, I'll let you know that later. And to find the expression, we usually in mathematics we need expressions. Okay, so to find the expression of R, scaled Rayleigh number, at which the transition from regular convective motion to chaos occurs, is called Hop Rayleigh number. Why it is called Hop Rayleigh number? Because in that point the complex conjugate is changed to purely imaginary. That's why it's a Hop bifurcation. That's why the value Rayleigh number at which Hopf bifurcation occurs we call Hopf Rayleigh number. To find the expression of that Hopf Rayleigh number, same thing we will do. That is, we linearize the Lorentz system around the critical point. Okay, whatever I have done this, same thing. So I took ABC has A bar, B bar, C bar. Notation is different, but the procedure is similar. Then this refers the critical point, that is root of B r minus 1. You can consider another pre-onset critical point also. Because of symmetry, anyone gives a similar answer, either this or that. Then linearizing the system around critical point. Let us first write this in the homogeneous system in the form of equation 34, and the determinant of L will give you the expression. This expression and the cubic equation both are same. Okay, and here the important thing is I will take lambda as I lambda. Why we need to take this? Many of us, even I didn't know beginning, then I come to know later. So why we need to take this is bifurcation, Hopf bifurcation. When Hopf bifurcation occurs, when the complex conjugate turns to purely complex number. That is why we have to take lambda as I lambda. So when you substitute f of lambda as f of I lambda and equating real and imaginary part, uh, and by this lambda will go off. So we'll get Hopf Rayleigh number in terms of some expression, that is PRB. And once you get this expression, you can change the liquid and see the RH for different liquid. For example, as I showed in our paper, that is CNSNS paper that is published very recently. In that paper, I took water, methanol, and I studied stability analysis KOs for water and methanol, and I come to some conclusion which liquid we can use, and stability and other things we discussed for those two liquids. Same way you can this property will vary with the liquid, so you can use different liquid, Newtonian liquid. Okay, and morning you already seen the phase space plot. Here I plotted for the transition from regular motion to chaotic motion. In the regular motion you have spiral, that is what showing in r is equal to 20. It is a spiral, and slowly spiral will change to chaos, that is it is spiraling in other critical point. So this will slowly lead to chaos. Okay, and in the point r is equal to 29.7, it is purely chaos. And as I mentioned earlier, we can study the behavior of the chaotic motion by using bifurcation diagram and Lyapunov exponent. In the bifurcation diagram, it's very simple. What we'll do is we'll take any one amplitude, we'll find out the solution of that amplitude by using any numerical method. It may be Runge-Kutta method or ND-solve. You can also use ND-solve in the Mathematica. So by using that, you can get solution of the Lorentz system. You take only a particular amplitude. It may be A, B, or C. Here I took C, and find the maximum value of that. That will give you the plot of that with R will give you the bifurcation diagram. And the bifurcation diagram here in from the point 0 to 29.7 refer to the regular motion. Okay, it's like a transition, as I mentioned there. It's like a transition from one. It's a regular motion. From there, it's slowly transit to chaos. And this dark blue refers to the chaotic motion. And in some points, like here, you're seeing a loop. And this loop refer to periodic motion. So here I want to emphasize this one. Okay, when we say after RH there is a chaos, it won't be in the chaos. The system won't be in the chaos for a long time. It will go to another motion that is called periodic motion. Sometimes in in engineering aspect, if you say that kind of transition from chaotic motion to periodic motion is maybe due to noise, some disturbance. Okay, so this limit loop periodic motion may reduce if we not disturb this system, but it's very difficult. It's very difficult to undisturb the system. Okay, there will be some noise, there will be some kind of perturbation will be there for the system. Those perturbation will indicate by this loop that is nothing but a periodic motion. So in this motion, how will be the phase space diagram that I have shown here, and it will be periodicity 5, 3, 4. That means you will see only 3 or 4 or 5, 4 or 5 chaotic, I mean butterfly diagram, spiraling. Okay, so it's depend on this point. If you take this here only 3, so it's a 3 periodicity 3. And another way of explaining this is by Lyapunov exponent. For Lyapunov exponent, you need to find the Lyapunov function that we can do by taking multiplying equation 1 and 2, that is Lorentz equation 1 and 2 by AB, 3 by this, and adding the, this is not a one way of finding Lyapunov function. We can find in many other way the Lyapunov function, but I'm sure that you will end up with the ellipsoid in the form of equation 44, even though you use another form of Lyapunov function. Okay, so that this means this region, the ellipsoid, is the trapping region. The solution won't go out of this trapping region, hence the solution of Lorentz model is a bounded. Okay, and we take Lyapunov exponent as the following way, that is equation 44. Okay, equation 44, and when tau tending to here y high, I referred for the amplitudes, and it's better I could have given some references for you so that you could have gone through this, how you will get a Lyapunov exponent definition as equation 45. I'm sorry for this. I will try to give, I have reference in the last, I can show you that. Okay, and maximum of this Lyapunov exponent will give us, once again, as we did for bifurcation diagram, here also the maximum one will show us, give us the nature, idea for nature of chaotic motion. Okay, and there are 3 Lyapunov exponents. The number of Lyapunov exponents is depend on order of the system. Since we have used the Lorentz system third order, classical Lorentz system, that is third order, we have 3 Lyapunov exponents. So maximum 1 will give us the information about chaotic motion and further periodic motion, and provided it must be a dissipative and sensitive dependence on the choice of initial condition. This sensitive dependence is because of Lorentz system. It even dissipative. I already showed you the dissipative nature. By adding roots, you will get same constant value with negative sign. That is nothing but a volume. So that indicates the system is dissipative. Hence, we can write Lyapunov exponents for this Lorentz system. And let us take some procedure for finding this liponomic exponent. Let us take define f1 f2 as this, and the variational equation as this, and substituting this variational equation and with this Lorentz system we will get lipono. And by using the equation there I showed you log 2, so by using that we will get lipono exponent. So I have plotted like maximum lipono exponent versus r. There are three lipono exponents, okay? And if you see all the three, the maximum one indicated by the blue line, so that only crosses the zero, that is positive value, that tells about to all like nature of the chaos. Okay, when the region, that is when R range between 1 to RH, then the maximum liponom exponent is less than 0. When R greater than RH, the maximum liponom exponent is very much greater than 0. So it goes up to 1 year. And this one, mildly chaotic, nearly periodic. This is a novelty in our paper that we published in CNSNS. So many have observed chaotic region, regular convective region, but there are some points. This is purely because of noise, as I mentioned you. So there are some points where the system is behave like mildly chaotic, nearly periodic regime. It is not a periodic, exactly periodic. It is not a chaotic. Okay, such kind of points we noticed in Lyapunov exponent, where the maximum Lyapunov exponent will be between 0 and 1. It won't be 0 or it won't be 1, but it's very close to 0. Hence, it shows behavior of periodic, and it won't be 0. Hence, it has mildly chaotic behavior too. Such kind of nature we observed in the for classical Lorentz system, and we named it as the mildly chaotic and nearly periodic regime. Then periodic regime, in the periodic regime, the maximum Lyapunov exponent will be 0. So for convective, non-convective regime, you can see the spiral, and spiral is outward here, so it is unstable. And this unfixed point or spiral is occurs when Lyapunov exponent takes this sign minus minus minus, or you can also refer it as maximum Lyapunov exponent is negative. Similarly, when in the chaotic regime, the maximum Lyapunov exponent takes the value sign positive, remaining 0 and minus. This is a periodic regime, and it has a periodicity 5. And in this regime, the Lyapunov exponents have sign 0, 0, minus. The maximum Lyapunov exponent in this periodic regime takes value 0. So same thing, that is the maximum Lyapunov exponent with periodicity I have included in this plot. And the periodicity may vary. Here we just varied. Okay, it may be periodicity 2 or 3, but that can be not predicted in Lyapunov exponent. For even periodicity 2 and periodicity 3 and periodicity 4, it shows same value, that is maximum Lyapunov exponent is 0. This can be captured in bifurcation diagram. That is the advantage of bifurcation diagram. And morning you might have seen the phase space diagram for sensitivity to initial condition. Same way we can also see in Lyapunov exponent 2. So here I varied the initial condition, and I noticed different Lyapunov exponents plots. Okay, so these are some references. Okay. So these are some references, you can go for it. And I think I still have Yes, I think I still have some. So I will discuss
You,
about this.
you,
Yes, sir.
you still have 15 minutes time.
Okay, sir. I will discuss few things about my papers, published papers. Okay.
Okay. Okay.
Thank you, sir. So whatever I have done in this problem, I took it from communication is non-linear science and numerical simulation paper. Apart from that, we have published a nice work in physics of fluids. So if you want to study the chaos between two same system with two different liquids, here we used multiple carbon nanotubes and aluminum nanoparticles with same system. Though the system is similar, same, and liquid is different, because of the properties of liquid we will see the difference in the chaotic behavior. Okay, that we have highlighted in our paper, that is physics of fluids. And those who would like to see the chaotic behavior between different nanoliquids, you can go for it. It's very good paper. And many of us usually do problem with the free boundaries, because of maybe it is very simple, and rigid boundaries give qualitatively same solution like free boundaries. But still we have done rigid isothermal, by taking rigid isothermal boundary conditions, same Lorentz system. But because of rigid boundaries, there are some coefficients. There are coefficients with the classical Lorentz system, and due to the coefficients, there is shift in not only the critical Rayleigh number and also Hopf Rayleigh number. There is a shift for Hopf Rayleigh number. So someone who'd like to study rigid isothermal boundaries, you can go for this paper. It's very well written. And the explanation for chaotic behavior, you can find it in Lagos paper. He have done it very well for ferroconvection, ferrofluid. So for cylindrical, whatever we have done is Rayleigh-Benard convection. One can apply same thing for cylindrical annuli and cylindrical enclosure. That you can find it in this paper. And these are some references for chaos and bifurcations. And for Laipunov exponent, I refer this book. It's very good book. And Sparrow is very good for understanding phase space plots. You may find in some papers they may plot the space plot, but you cannot find the difference in the two plots. That can be done if you refer the book by Sparrow. You can find out the difference between two Lorentz system. There will be some difference, but without understanding the problem, it's very difficult to find the difference. That you can do by seeing Sparrow's book. Thank you. If you have any question, please you can post it.
Yeah. If anybody is having any questions, please you can ask Dr. Kanchana, or otherwise you can post it in chat box also. I'll give 2 minutes for this. Hello. I hope all the faculty are not having any doubts.
I think there is some doubt. Someone posted.
Dr. Shilpa is asking, ma'am, can we use this work to boundary layer?
Yes. Yes, I think. In the boundary layer also you will get a dynamical system, autonomous system. You can go for this method, same similar method there also. You can do. And I already told you I initiated the work of this for higher modes. Many of researchers didn't go for higher modes because the linear stability analysis that threshold will be similar behavior we will see for higher modes. But when we go for chaotic motion, there is a difference. Okay, when we go for higher modes, so those who would like to study the chaos, it's better to see for minimal mode and higher mode. Then when you start increasing the modes, after some particular modes, you will see once again the similar behavior. Once again, you will see the similar behavior. There you have to stop. So such case, the minimal mode of linear stability won't be the same as the minimal mode for chaotic motion. That you can study and do. That I'm doing. Maybe this year we may publish that paper too. And I'm giving idea for you people to do that. It's very nice work. And the plots I have plotted in the showed in the slides, and it may look very um, simple, but especially the lipono experiment plot, it's very difficult to do. And in my laptop, I took more than 24 hours to plot that. So recently, I'm using parallel processing system. But if you want to do in your laptop, you must have some patience to plot that bifurcation diagram and Lyapunov experiment. And if someone is interested to do this problem and plot, you may contact me. I have some nice programs, and I can share you. That I took from internet only, and I modified that for my paper. So I will share that to you. You can do it for your problem.
Yeah, as Dr. Kanchana said, many of the participants here definitely they will be in touch with Kanchana. They can work with her at University of Tarapaca at Chile. So they have got a nice opportunity for their postdoctoral work, I believe. Anyway, it's okay. So morning session was also chaos and this session was also chaos. I hope the next session will not be a chaos. It is a ferrofluids. So definitely people, I think all the participants have shown keen interest on these two topics. Certainly they will contact you, madam. Please be helpful to them. Your session was a wonderful session. Thank you for giving a nice lecture. With this, I'll end the session now. So at 3 o'clock, 3:30, 3:20 now, 3:30 we'll join again and we'll listen to the new topic, ferrofluids, by Dr. Annama Abraham of BMS IT. Thank you. I'll end the session now. Please join us at 3:30 sharp.